Happy snow day! So I'm going to do some more videotaping so we can keep up speed. I'm going to do the last problem that I got cut off in class for Integration 5, and I'm going to do a couple of the problems from Integration 5 worksheet because I still am going to collect that on Monday, right? Integration 4 and Integration 5. Obviously the problems that I picked to do with you here, I am not going to pick those ones to grade, but hopefully you'll see me do a couple and then you'll be all good. And then, yes, there is going to be a third installment because I'm going to have to give you Friday's lesson, which is integration by parts. So that will be installment number 3. So, also, I have a cool new slate so that instead of having to watch me write the problems out on loose leaf paper, you can see me actually write on my computer screen. But of course, we still are taping a computer screen. So let's move over here. Yay. So this is the last example that we had in class where I said that I had looked at this problem, thought about u substitution as 9 minus x squared. Maybe that would be my u, but with a derivative of negative 2x and no negative 2x to find inside the integrand, I had to think of something else. So I thought to myself, maybe this is inverse trig, since I have a 1 in the numerator and a root 9 minus x squared, and it's only this 9 that is kind of in my way. So I thought of factoring. Good old algebra 1, right? So I have dx on top of the square root of factor out of 9. Factor a 9 out of 9, I get a 1, because actually the d word that goes with factoring, the f word, is divide. So 9 divided by 9 is 1. X squared divided by 9 is x squared over 9. Using my property of the square root of a product is the product of the separate square roots, I can take the square root of 9 multiplied times the square root of this expression here and say that's 3 times 3 times 1 minus, and then I'm going to do some more rewriting and say x squared over 9 can be written that way. When I see it this way, I realize, yes, I think I can fit this into my inverse sine formula, and I'm going to make this my u. To do that, change my color, and if I make u equal to x over 3, du is 1/3 dx. Now normally, I look at this and I say I'm going to get the dx by itself because I have dx over here by itself, or do I? That's 1/3 dx right there, and I have 1/3 dx here, so I can just do a direct substitution. So I can do du over the square root of 1 minus u squared, which fits into my antiderivative formula, plus my vertical shift. And I have to put my u stuff back, since this is an indefinite integral. So this is going to become inverse sine of x over 3 plus c. Yay. So realizing that when I looked at this integrand to begin with, that it was white screen, and if you look at number 1, whoopsies, number 1 from integration worksheet number 5, it's a log problem, a log of a different base other than base e. And it was a definite integral. log base 10 of x. Of course, when I have base 10, I don't really have to write that 10 now, do I? And it was going from 1 to 10. I am going to take this part first and rewrite that before I do any calculus. So here, algebra 2 is coming to my rescue. So I'm going to rewrite what's in what I've highlighted as ln x, so changing to base e, over ln 10, which is just a constant, so it's about to osmosis. So I'm going to take the 1 over ln 10 and move it out here. And then I have what looks an awful lot like the warm-up we did yesterday, where, using u substitution, I'm going to make ln x my u, and the derivative of ln x is 1 over x, and then multiplying, of course, I get my dx. So I have a straight substitution of u and du. Right now this 1 and this 10 are still x values, but since u is ln of x, well then these limits then as u values are ln 1 and ln 10. And I'm just integrating u du. So look back at this original, right? Look at this original problem. Logs, base 10, dividing by x, you know, But in reality, when I do, as long as I recognize and do some rewrites, I'm integrating u to the first. And integrating u to the first is just my old power up, u squared over 2, plus, nope, don't need plus c. And I'm at ln 1 and ln 10. But don't forget that I still had my 1 over ln 10 there, so of course I have it here as well. So using the second part of the fundamental theorem, I have ln 10 squared over 2 minus ln 1 squared over 2. But we all know that the exponent that turns e into 1 is 0. 0 squared is still 0, and 0 over 2 is 0, so bye-bye. ln 10 squared is, of course, ln 10 times ln 10. Bye. And I end up with ln 10 over 2, which is a perfectly legitimate answer. I leave it alone and move on if I'm doing my own work, writing out my own work. But if this is multiple choice, I think to myself, this answer could be there. Phone, ignore the phone. Who answers landlines anymore? 1/2 ln 10, which of course could be ln 10 to the 1/2, or of course ln root 10. Whatever. Okay, as long as I recognize different forms, I'm good to go for multiple choice. Alright, that was number 1. Let's do, the other one I picked out was number 9. Number 9 I picked because it had another one of those algebra tricks. So my limits of integration were 0 and 1, and it was 4x over the square root of 4 minus x to the 4th. So again, since I'm dealing with inverse trig, I pretty quickly ran through and figured out this was most like, again, inverse sine. I have an x to the fourth. I wasn't too worried about x to the fourth because I know I need 1 minus something squared. But that 4 was in my way. Dividing 4 by 4 again gets me 1. Dividing x to the fourth by 4 gets me x to the fourth over 4, but I want to write that as something squared, so x squared over 4. No dippy. 2. X squared over 2 is x to the fourth over 4. So, if now I think to myself, self, that's you, meaning du is 2x over 2 but the 2's will go away, so I just have x dx. Here's my u, here is my du, so 4 can osmosis out here. This 4 is going to come out of my radical, just like I did with that last problem, as a 2, and it will osmosis out here, leaving me with 2 outside the integral, and x dx is du. I have my radical, and I have 1 minus u squared. My limits of integration as blue u numbers. My upper limit as an x was 1, so if I put 1 down here, and take the lower limit 0, what is that? I can now fill in 0 and 1/2 there. Yep. So integrating, I have inverse sine of u at 0 and 1/2. The arc that has a sine of 1/2 is pi over 6. The arc that has, excuse me, a sine of 0 is 0. And 2 times pi over 6 is, of course, pi over 3. Yay. So another example of where I had to do a little bit of Algebra 1 first before I was able to use my formula sheet, where I could just recognize inverse sine. I picked number 11 as my next example on integration 5 because it looked so awful to begin with. Had all kinds of crap going on. I think that one of the best techniques, I guess, that I use when I'm integrating is to look at problems in pieces, not be overwhelmed altogether when I look at the problem. So when I looked at number 1, it's a definite integral with a fraction, 2 dx, and then in the bottom I had all kinds of stuff going on, 1 plus x squared and freaking inverse tangent in a denominator of all things. And my limits of integration were 1 to root 3. So, again, overwhelming if I look at this all at once. But some things I recognize is when I'm assigning somebody to be u, I'm looking for its derivative. So if I thought about 1 plus x squared, its derivative is 2x. Oh, I have a 2. Oh no, it's just a 2, not a 2x in the denominator. And I can't just be randomly sticking in functions into my integrand. But when I looked at inverse tangent, which was not my first thought, and I said, well, I got nothing else, so if I say u is inverse tangent, what is du? 1 over 1, wait a second. Here is 1 over 1 plus x squared dx. The 2's in my way, which is okay, because osmosis. And there I have du, and then I have u. So put my 2 out here, du on top of u. Of course, I can look at this as u to the negative 1 du. OMG, here comes the natural log. So, right, stuff to the negative 1, I can't power up. So, there I go. Who knew? I had 2, a fraction, 1 plus x squared, inverse tangent, all in the denominator. Hello, Mr. Getz. Oh, all right. I need, yeah, I'm almost at the end. I'm doing the last problem.
Okay.
We gotta go. So this is, all I have to do is my limits of integration. So 1, if I do u of 1 over here, the arc whose tangent is 1 is pi over 4. And u of root 3, the arc whose tangent is root 3 would be pi over 3. So those are my limits of integration. I don't need my absolute value bars because pi over 3 and pi over 4 are already positive. Ew, this looks pretty ugly. Again, I leave it here. I leave it alone if I'm doing multiple choice. I'm sorry, if I'm not doing multiple choice. I could see this in multiple choice this way, using log properties. Cleans up a little better. Which, oh my gosh, if I'm being really super industrious, right, I could say that's, what, ln 16 ninths, right, if I bring up the 2 there. So, any one of these I'm just worried about for multiple choice. Long answer, I'm pretty much going to stop here. Now, I was going to do one more, and so before Mr. Getz yells at me, because we have to get going, I'll just set this one up. I was going to look at number 12. And really, the only reason I was going to look at that was for an Algebra 2 problem. or a piece, I should say. I have e to the x's all over the place. I tried a bunch of things before I got to inverse tangent, but inverse tangent needs 1 plus something squared down here. But because I took Algebra 2 and paid attention, I know that if I have e to the 2x, I can write that as e to the x squared. So, and shockingly, if u is e to the x, what is du? Why, it's e to the x dx. So there's du, and here is 1 plus u squared. Because this is my u. So that is inverse tangent of u, and of course e to the 0 is 1, so my lower limit is 1. And u of ln root 3, here comes algebra 2 again, e to the ln root 3. Hello, inverse operations. Number one fun fact of inverses, they undo one another. So this is just root 3. So I have inverse tangent of root 3 minus inverse tangent of 1. Hello, algebra 1, get a common denominator. No, I mean elementary school. And I get pi out of 12, pi over 12. Yippee! Uh-oh, I hear him coming. I'm coming! Bye. Watch out for next time, coming back soon to do integration by parts. Jazz hands!